Alright, so in this video, we're going to go over the basics of Faraday's law. So, what Faraday's law states is, if we have some kind of closed path, and we integrate the electric field over this path, right? And when we integrate, we have to be careful that we're only taking the portion of the electric field that is actually along the path. So that's why the integral takes the form of E dot dl, where dl is some infinitesimal portion of the path, and we just want the electric field to be parallel with that portion. And the reason why it has to be a closed line integral is because we're relating it to a flux. And if you think back to Gauss's law, right, the flux of a field through a surface is only, we're integrating the portion of the field that is actually perpendicular to the surface. So you can think of it as the amount of the magnetic field that's flowing through our surface. And the path that we integrate over is the boundary of that surface. Well, if I have this, that doesn't enclose a surface. Like, what is the surface that you're asking me for? You haven't defined one. That's why it has to be a closed path. So now let's go over a simple example of Faraday's law. First we're going to write it out. Nope. The closed line integral of the electric field is equal to the negative rate of change of the magnetic flux through the surface bounded by this curve. So let's say I have a circular loop of wire whose radius is r. And I have a uniform magnetic field going into the board, inside. It's uniformly distributed, and I'm going to have it increasing linearly with time. So the magnetic field as a function of time is going to be some initial value plus B1 of t. And both of these point into the board. B0 points into the board, B1 points completely into the board. So basically it's just getting stronger in this direction. Now this negative sign, where is that going to come into play? Well, think about the way I'm going to do the axes. Let's say I define my axes this way. This is the x, this is the y, and the right-hand rule will tell us which way the z-axis has to point. So x, y, z has to be pointing out of the board. So basically our magnetic field is pointing in the negative z direction. And when we do an integral like this, it's considered to be positive if we're going, when we do a flux calculation, it's considered to be positive if we're going through the surface such that we're tracing the boundary in the counterclockwise direction. Right? So, right now, my magnetic field is pointing into the board, and it's getting stronger in the direction that is going into the board. So if we negate that, it points out. And then the right-hand rule, that aligns correctly with the right-hand rule, because then we can expect, we get the positive answer by integrating counterclockwise. So we won't worry about the axes anymore. That's all we needed to talk about the axes. And an easier way to think about that is with Lenz's law. So, even though we're not going to calculate the voltage yet, we can still think about which way it's going to go. So the charge is going to flow either clockwise, or either counterclockwise, or clockwise. And our magnetic field right now is pointing into the board, and it's getting stronger in this direction. Lenz's law says the magnetic field generated by the induced current. So as the current in this wire flows, it creates its own magnetic field. The direction that that field is going to point inside the loop is going to be in the opposite direction of the change in the magnetic field. So my magnetic field is getting stronger in the direction that's pointing into the board. So my induced magnetic field, the one created by the induced current, better be pointing out of the board. The only solution where that happens is when we have the current circulating counterclockwise. Now we're going to do our calculation. First, we need to find what phi of B is, or phi of B. Well, since it's uniform everywhere, that just ends up equaling B of t times pi r squared. Right? So now we need the rate of change of B of t. Oh, one small technicality, right? B is pointing right now in the negative z direction. Our surface is oriented so that positive is in the positive z direction. So the flux right now is actually negative, right? So basically, when you have a surface, right, say this is the surface of our circle, right? If the magnetic field is pointing this way, we get one answer. If the magnetic field is pointing this way, we get the same answer, but obviously it should be opposite in magnitude. How do we decide which one's positive and which one's not positive? And it's just a conventional thing, right? Consider if I'm looking at the surface such that I'm circulating around it counterclockwise, that direction is positive. So since this points in the negative z direction, but my surface is oriented so that positive is in the positive z direction, flux is actually negative. So now I need the rate of change of the magnetic flux over time. Well, that just equals, what's the derivative of this with respect to time? It's just b1. That's just b1 pi r squared. And then there has to be a negative sign. But if I'm going to take the negative rate of change anyways, I just negate both sides, and that actually becomes a positive answer. Again, positive in this case means our voltage goes counterclockwise. So the induced voltage is just going to be b1 pi r squared. And that's pretty much all there is to Faraday's law.